Right, hello, my name's Simon Bingham, and this is part of my series on routing policy and Junos. I think as you approach the advanced topics, it's sometimes a good idea to sort of remind yourself of some of the basics, and this is what this video is really aimed at. So what I found is, as I was looking at some of the routing policy, I was just kind of scratching my head trying to remember, what we're doing here. So this video really is to demonstrate subnetting and provide us with a basis for some of the rather more complex route filters that Junos provides to match what's in the routing table. And if you have an understanding of this little diagram here, it will really help you tremendously with understanding what addresses Juniper is going to match. Now, what do we have in a routing table? Well, a routing table is, in essence, a description of a network number and the mask associated with it. It's a network and net mask, or prefix and net mask as it's called. So what does a net mask mean? Well, a net mask really is what indicates what portion of a network address is the host portion and what portion is the network portion. So if, for example, we take a well-known slash kind of, a slash 24, which is sort of a well-known network mask, and we look here. So I've drawn out the network mask in full. This is really saying that it's going to look at all these bits here and compare it with the address that we have. If we wrote out this address here underneath it, and it's going to determine, and I'm not going to go through the maths here, but it will determine that 10.1.1 is the network portion, and all the rest of the last octet is left available for host addresses. Now, it doesn't have to be like this. We can choose, if we want, a different mask and subdivide this particular network differently. So if we decide that, oh well, we don't want to use all those addresses, we'd rather have two different networks with half the number of addresses, we can do that. So we simply make the mask one bit longer, and then we'll have two networks available to us. One starting at 0 through to 127, and then 128 through to 255. Now, this logic continues. If, say, I decided, right, I've got one network here, and I don't want to use this 128, I want to divide this down into two different networks. Well, you could have another network with 128 going up another 64 addresses, and say 192 going up to another 64 addresses. But hey, I tell you what, I think 64 addresses is too many. I want to divide that into two lots of 32 addresses. Well, you could do that again. So, and you can continue this logic. So what I've shown in the red here is actually a feasible and completely legal subnetting of a slash 24 into every possible network mask. So none of these network addresses overlap here. So a 128 goes up to 191, and you can just complete dividing this down. So none of these addresses in the red would overlap. So why can't I? What do I mean by that? So why can't I say have all these networks, say on the left here, available at the same time? Well, though they overlap, that's the answer. So if I want to have a 10.1.1.0 slash 24 and a 10.1.1.1.0 slash 25, so why won't that work? Well, simple fact is they live in the same space. So if you think about it, the address, you've got the same address space. So a 0 here is a 0 here. You couldn't distinguish between the two networks. So that's not legal. So Juniper has a number of statements inside route filters, inside routing policy, which determine the addresses that you're going to match out of the routing table, and I'll cover these in the next video. But it's important, very important, to keep this in mind when we're looking at what we were going to match out the routing table. Right, routing policy. So what is a routing policy? Well, a routing policy allows us to determine or influence what is coming into the routing table via an import, and what comes out of the routing table by what's called an export policy. So this allows us to do a number of things. I won't go into all the protocol specific stuff here, but I'll just give you some examples. For example, you could say a route coming out of BGP, I want the next hop to be myself. Or you could say I want a route coming basically out of the routing table into OSPF. So I say I want to write an export policy for OSPF to say export a directly connected or export a static into a protocol. Right, I've just mentioned there's two quick statements here which are tremendously useful. These are show route receive protocol and show route advertising protocol. Now these tell you what is coming into the routing table and what is coming out. So it's very useful because you don't have to look on the next hop router to see what's being advertised to it. You can see it right here from the horse's mouth, so to speak. Now, in terms of import policy, there's a little complication here. Now that is that link state protocols work slightly differently. So link state route, when you configure a link state routing protocol like OSPF or like IAS, that's where you configure in effect the interfaces it's going to be running on, right? So you're not really importing something into OSPF, you're telling it what to run on. Now OSPF will then run on all these interfaces and then it will draw a map. Or in effect, it talks via LSAs, right, to all its other routers, saying this is my view of the world, right? I've got a router here and I've got these connections. Another one says, I'm a router and I've got these connections, or here's a network, and then it'll send out a network LSA. This is my view of the world. All that really matters is you get an overriding map that OSPF understands. Now, OSPF then runs that map from each router's point of view, or looks at that map from each router's point of view, and then puts that in the routing table. Now, you don't really want to influence that because OSPF has already done its own thing there, and you know, every router has to have its own map, has to have the same map of the entire network, otherwise we'll end up with problems. There's a bit like, imagine road signs maybe saying contradictory things. All the road signs have to point to the right place. So the export policy, again, that's what comes out of the routing table into a protocol. Yes, that can be configured for all the protocols. Right, to continue our discussion about routing policy and route filters. Now, a route filter is probably the most important part of a policy statement, and let me just give you a quick example here that I've got running. So this is, you don't really need to understand the full logic here, but I've got a routing filter here called into a particular autonomous system. I'm saying from protocol direct, match these particular routes. Now, it's extremely important to understand the logic in terms of exact or longer, and I'll run through all of them now. So what I've done here is, you see my diagram here, I've actually created every single route on here as a static route on a device on my network, and I've redistributed this into a routing protocol. And then at the point where the routing protocol gets, routes get sent to another device, I'm going to write a routing policy to change the metric on them. So they're all there, but the routes that we act on, we will see the metric change. So the first of the routing filter statements I'm going to look at is exact. So let's match on this one exactly. Well, what exact is, it's fairly simple. It's as you'd expect. It matches on the exact prefix and the exact match. So if, for example, we match on, say, 10.1.1.0/26, then that should be the only route that gets, in effect, affected. So let's have a go at this now. Let's have a quick look. So let's do edit term testing. Let's do set from route filter. And what did I say again? I said 10.11.11.0/27. 10.11.11.0/27. Oops, and I missed the exact point. Do a show here, so do a commit. So we're going to set the metric of that route to that, and just to prove a point here, let's just commit this. Show route 10.11.11. I'm just going to show you what's in the routing table. So you can see here we've got loads of these routes in here. There we go. So you can see all these routes in here from that diagram. So let's have a look at what we're exporting to our neighbour. So let's look at what we've matched on. Now if you just look at my statement here, all I'm doing is I'm saying if it's a BGP route, you don't have to really understand too much about this, other than we're looking through our routing table, we're matching on 10.11.11.0/exact, that's /24 exact, and we're going to change the metric. So let's see what we're exporting to our neighbour. There we go, exact. Now let's just pick another one from here for completeness. So let's pick the 10.1.1.192. Oh, we see two. So it's these ones that have got the metric of 11. So there we go. We matched it, and we matched it again. So that's the exact statement covered. Right. Let's look at the or longer statement now. Okay, referring back to this diagram again, we've got all these routes in the routing table. Let's use the or longer. So what the or longer does is it matches on, you're basically saying 28, match on 28, and then longer prefix /29, and then longer prefix /30, and then the longer mask, then so on like that. So anything that's after this. So if we match on, let's say for example, in our example here, let's match on 10.11.11.12/30 or longer, so we should be matching all these ones underneath. So let's give that a go. So it was again 10.10.11.11.12/30 or longer. So let's have a quick look at what we're matching. So let's have a quick compare this to our diagram here. I hate it when that happens. So we've got the 12/30 matched, then we've got the 31 matched here, we've got the 32 matched, and then we've got the 13/32 matched. Yeah, you can see that's worked actually. Have a quick look at that. We can see the 14. You can see the 14 is matched, and 31/30. That's matched everything or longer. Right, let's have a look at the or longer statement now. Sorry, the longer statement. Now I'm going to use the same address here. I'm going to write longer instead. I'm going to commit this and see what we get. So or longer basically looks for the prefix and then tries to determine whether the mask is longer than 31. So in this case, it will look to see if it matches that, a /30, so all addresses that fall under that, but then it will say, are you a 31 or are you a 32? So the reference to our diagram is going to match anything that falls under here, but it must be longer than 30. So it does not match a 30, but it will match the 31 and the 32 and all these ones. So we should see the 6 under here. Did I commit that? Yes, I did. So let's have a quick look at what we've got, what we're sending to our neighbours. So we can see here, I'll show this, you can see here that the 30 is missing and the 31 and the 32 is all under that triangle. I'm missing. Now there is a massive gotcha here, and I'm going to just keep going on and on about this. The logic here is somewhat bizarre if you have multiple terms. So you see this term here. So what it actually does, if you had multiple terms in here, you had another root filter statement below this, what it would do is it would find the closest match. So if I had another more wider term here, let's actually show you. Let's actually do this. So let's do. I think how I can demonstrate this. So what I'm going to do here is I'm going to put another statement in here that's going to be wider than this. So I'm going to do an or longer on this address here, but I'm going to leave the longer here. And I just want to show you something. This is a bit of a interesting one. So set term testing from root filter. So what have I got here? I've got two statements here. So what's going to happen if I have a root which matches exactly on the 10.11.11.12 prefix? So if I have a 10.11.11.12 come in as a /32, what's going to happen? Well, I would say common sense might dictate that it doesn't match that, and so it moves to the next one. That's not how the logic works here. The logic works is it looks through this for its closest match. Okay? So it will look through and it will say my closest match, just looking at this statement here, and it will say, ah yes, I do have a 10.11.11.12, it's here, I've got it, /30. Is it longer? No, it's not. Then what does it do? It then moves to the next statement, completely missing this out completely. So it's a bit of a weird logic that, and you know, it's one I would make sure you know about, because I would imagine they love testing on this kind of thing. So let me get this through. You go through the logic again. If what it will do with this match here, just this one here, it will say yes, I have a match for that, but it's not longer, so I'm going to go to the next term. Now the others, these, it will still match it. It'll still match them because it will say, oh yeah, I've got a match and I'm longer. But for this particular one, it won't. So let's just prove the point. Now look here, this one is missing because all these ones up here, so these are matching on my first term, which was to match this address or longer, so they all fit under that. But the closer matches, these ones, actually fall under my longer statement, which is the ones that are matching here. And not only that, they miss out that one because it's saying, well, I do have a match, but I'm not longer. So that's an interesting kind of logic there. Okay. Now let's look at the up to statement. The up to allows you to determine the basically the range of masks. So let's say I want to do all the addresses under here, say under 10.11.11, but miss out the /32s. Tell you what, let's do a 10.11.11 slash let's keep it simple, don't get too many roots. I'm going to choose this one and I'm going to say all the way up to the 30, so we'll do 26 to 30. Right, so let's go set root filter, let's say from 10.11.11.0/26 up to .30. Do a commit and see what we get. So let's look at what we get matching here. There's 11. Remember, we're matching and changing the match 11. So we get the 26. We get this one here, the 27. We get the 28. Then we get, so look, the two 29s, the 2/11.11/8 is matched. 29, and the other one is matched here. So that one is matched. Going down the tree, the 29 is matched. And going down the tree one level, we'll expect to see the 10.11.11.0/30 matched. And then we can see the 10.11.11/12 matched. Yay, and it is. And none of the others. So if we go further down the tree, for example, we look at our 10.11.11.12/32, 10.11, they're not matched. Okay, so that's the up to. Okay, the next one I want to cover is prefix length range statement. Okay, now this is a bit of an odd one. This allows you to define a initial prefix and mask. So you're saying I'm interested in everything that falls under it. So say here I could do everything that falls under in this sort of slightly subset triangle, or in all my addresses. And then, but you can say the second part of this, I'm only interested in particular prefixes. So let's say, for example, I want to single out all these roots, all my roots that are between 28 and 26, but none of the others, but anything under here that's between 26 and 28. Let's go and configure that. And I think this is an ISP type thing, where ISPs might want to say we want to ignore the most specific roots. So let's set that up now. Set root filter, and in my case I think I'll do my whole tree. Right, prefix range length, and let's choose, say, just to make it easier for us, let's choose 26 to 27 /26. So we're going to ask it to return all the roots that match that. Okay, so let's have a look. We expect it to match the. It doesn't match the initial. Well, let's look. So we're gonna. What did we say? 25 to 26, didn't I? Right. So let's have a look. We've got the 25. Have we got the 25 in? That's interesting. That's not there. I did 26 to 27. Let's have a look. What did I do? Oh yeah, 26 to 27. That's why it's not there. Okay, so let's have a look. We would expect to see initially we've got to accept these three, so the 26's. So we've got the 26, we've got the 128, 26 is there. The 192 26 is there. There's one other 26 one, which should be this one, the 0. The 10.11.11.0.26 is there. Now we should only see the 27s. So another 3 there. So we've got the 0.27, that one. Then we should be the 192.27. There it is. And finally the 224-27. That one. There it is. Okay. Next one I'm going to cover here is going to be the through. Now this is a bit of a peculiar one. What the through covers is the through will cover. It's almost like if you tracked back. So if you started at say a particular address, a mask, and you went, well, what sort of? It says if you went through this tree, it matches all the ones that match. And I personally can't think of a practical application for this, but it exists, and it says in the books that it's something to do with the corner case. But let's say we're going to track back and match all these ones here in this path. So let's go that one, that one, that one, that one, that one, that one, and that one. Let's match them all. I'll tell you what, let's miss out the 32, so let's just do those. So we're going to match from there, from there, from there to those, but none of the other sort of families that come under that. So let's do that. Let's do 27. So that's 27, and let's match all the addresses through to 10.11.11.12/32. That's like 31. Does that work? Right, let's see what we've matched again. I've not matched anything. Let's have a look. Must be a typo. There we go. Typo in there, look. Delete. It's more trouble than it's worth to try and edit it. So what have we matched on here? So the highest we've matched on the, oops, sorry. It's a bit easier to read and scroll down. Right, we've matched on 26, the /26. We've matched on that. Is that what we intended? Let's have a quick look at that config again. Oh, that's interesting. Oh no, we haven't matched on the 26, I just read it wrong. Okay, so the 27 is matched, the one below it is matched, the 28, this one. Then, what else do we have a match on? We have a match on the 829, which is there. Then we have a match on 12.30, that one, and the 31 and the 32. Oh, we don't have a match on 32, I'm reading it wrong again. So there we go, so that looks like that's worked. Now, if your head is hurting, I'm now on the final one. So what I'm going to do is show you the address mask statement. Now what the address mask allows you to do is allows you something a little bit more funky. You can use something called non-contiguous mask. Now this is probably going to make your head hurt, but you can see the example here where I've got the masks going all the way from left, and we all think that a mask works, right? It starts with ones, ends in zeros. Well, what these ones represent is things we're interested in, things we're matching on. So we're matching on that for what we want to match. So let me try and demonstrate this as a bit of a funky example. What I'm going to do is I'm actually going to pick out the addresses with odd numbers in. So it's going to be the subnets with odd numbers. So what we could do is we could do set root prefix, root filter 10.11.11.0/24. So I'm interested in all my addresses. Only the ones at the bottom will have odd numbers in, because that's the way it works. I could do address mask 255. I made a mistake here, right? So what I have to do is tell it that I'm interested in things with a 1 in the very last bit. So it will be things that end in 0000001, whatever that is, 7 zeros and a 1. Address mask. So let's think about what we're doing here. We're saying it has to start with 10. It has to have 11 in it. It has to have another 11 in it. And it has to have anything, so it can be anything between 0 and 255, so long as it's got a 1 in the end. So that way we do this. Probably not a mask you've seen before, eh? So I think this will work. I haven't tested this recently. Right, let's have a look at what it's matching. No, it hasn't worked. I'm going to have to go and have a look at that. Okay, thank you. Okay, I'm back and I found out my mistake. So let's have a look. I'm showing you here. So I changed that from a 24 to 32 because it's in effect an exact. So what this statement says is find the addresses with an exact match for 32 prefix. Only the 32s are considered in my case. Then run it through this mask, and in effect, because I've got a 1 on the end, I'm saying if it matches 10.11.11 with an odd number on the end here, this is I have to put the 1 in here, because if I did a 0 here, it would only match evens on the end. Then match it. Now, I'd like to see if you ever need to use that, but I guess I could see a use for it in terms of load balancing. So you could do something where you could balance certain prefix. And if we look here, we will see that our /32s with odd numbers on the end match. Okay, right, that is finally it.